Hello, this is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
This video is about the fundamental working principle of the alternator. We are going to determine the expression of the electromotive force induced in the rotating coil, determine the expression of the voltage across the terminals of the coil, calculate the number of turns in the coil, determine the direction, expression, and amplitude of the current induced in the coil.
The shown figure is a diagram of a simple alternator. The coil of an alternator is placed between the poles of a U-shaped magnet. The magnetic field between the poles of the magnet is vertical, uniform, and of magnitude 0.4 Tesla. The coil of N turns, each of area 100 cm squared, is oriented positively from D to C. At T0 equal 0, the angle between the unit vector N normal to the plane of each loop of the coil and the magnetic field B is theta 0 equal 0. The coil is made to rotate at a constant angular velocity theta prime equal omega about a horizontal axis delta. An oscilloscope is connected in order to display the voltage UDC. Number 1. Prove that an EMF is induced in the coil and that the coil does not carry an electric current. During the rotation of the coil, the angle between N and B changes, so the magnetic flux crossing the coil changes. Therefore, an electromotive force is induced in the coil. Now, what's about the current? Since an oscilloscope is connected across the terminals of the coil and the oscilloscope has a very high resistance, therefore the circuit is open and it does not carry an induced current. Number 2. Determine the expression of the angle theta between B and N in terms of T and omega. Since the coil is in uniform rotational motion, or since the angular velocity theta prime of the coil is constant, so theta can be written as theta prime t plus theta 0. Theta 0 is the initial angular abscissa, which is equal to 0 given, and we know that in uniform rotational motion, the angular velocity is equal to the angular frequency omega. Therefore, the angular abscissa theta can be written as omega times t.
Let's move to part 3. Determine the expression of the electromotive force induced in the coil in terms of N, omega, and T. The expression of the magnetic flux crossing a surface due to a uniform magnetic field is given by NBS cosine theta. Now, B is equal to 0.4 Tesla. The area of each loop is 100 centimeters squared, which becomes 100 times 10 to the power minus 4 meters squared, and theta is equal to omega t as shown in the previous slide. Now we want the expression of the electromotive force, which is given by Faraday's law. So we need to differentiate the above expression with respect to time. N times 0.4 times 100 times 10 to the power minus 4 is constant, so it stays the same. Now take omega t as u. The derivative of cosine u with respect to time is equal to minus u prime sine u. So this is going to be minus 4 times 10 to the power minus 3n into minus omega sine omega t. So this is the derivative of cosine omega t. This is going to be E is equal to 4 times 10 to the power minus 3 n omega sine omega t Si. Let's move to part 4. Determine the expression of the voltage UDC in terms of N omega and T, and then deduce the shape of the voltage UDC. Now look at the figure. The loop is oriented positively from D to C. So UDC is equal to Ri minus E. Remember, the expression of the voltage across the coil depends on the chosen positive sense and not on the direction of the current. Now, I is equal to 0 because the circuit is open. So we still have UDC is equal to minus E. and E is given in part 3. So this is going to be minus 4 times 10 to the power minus 3 n omega sine omega t. Now, what is the shape of this voltage? The shape of this voltage is alternating sinusoidal because it has the form E UDC is equal to a constant multiplied by sine omega t.
Focus, please. This is important.
Part 5. The adjacent graph represents the voltage UDC as a function of time on the screen of the oscilloscope. Given that the vertical sensitivity or the vertical gain is SV equals 77 volts per division, and the horizontal sensitivity or the time base is VB equal 4 milliseconds per division. Questions: determine the value of the angular frequency omega of the rotation, and then deduce the value of the number of turns n of the coil. Let's determine the value of omega. To determine the value of omega, we have to determine the value of the period of the rotation t. So that t is given by this formula, t equal x times Vb, where x is the number of the horizontal divisions measured over one cycle. As we see, x is equal to 5 divisions. Let's count the value of x. 1, 2, 3, 4, 5. So replace x by 5 divisions and Vb by 4 milliseconds per division. Therefore, the period is equal to 20 milliseconds. But omega can be given using this formula. Omega equal to pi over t. So replace t by 20 times 10 to the power minus 3 seconds. Therefore, omega is equal to 100 pi radians per second. Now, let's determine the value of n. From the previous slide, UDC is equal to minus 4 times 10 to the power minus 3 n omega sine omega t. But the absolute value of minus 4 times 10 to the power minus 3 n omega represents the maximum value of the voltage UDC. So, UDC maximum equal 4 times 10 to the power minus 3 n omega. Now, replace omega by 100 pi. Therefore, UDC maximum is equal to 0.4 pi n. But UDC maximum can be determined graphically using the graph according to this formula. UDC maximum equal SV times Ym, where Ym is the number of the vertical divisions for a positive or a negative peak measured relative to the time axis. We observe that Ym is equal to 4 divisions. Let's count the value of Ym. 1, 2, 3, 4. So replace Ym by 4 divisions and SV by 77 volts per division. Therefore, UDC maximum is equal to 308 volts. Now we can write 0.4 pi n is equal to 308. Therefore, the number of turns of the coil is equal to 245 turns.
Let's move to part 6. The oscilloscope is replaced by a lamp considered as a resistor of resistance 200 ohms. The resistance of the coil is 20 ohms. Look at the figure. This is the lamp. It is connected across the terminals of the coil. Now, during the rotation of the coil, it is crossed by a variable magnetic flux and becomes the seat of induced electromotive force. And now, the circuit carries an induced current because it is closed. Now, we want to apply Lenz's law to determine the direction of the induced current during the rotation of the coil in the first quarter cycle, which means that the angle theta varies between 0 and pi over 2 radians. Now, initially, the coil is in the horizontal plane. Look at the figure. We draw the coil in a certain position during its rotation counterclockwise in the first quarter cycle. Now, first, so remember, the coil rotates counterclockwise. Now, according to Lenz's law, the created Laplace forces acting on the sides of the coil tend to resist the rotation of the coil. Look at the figure. These are the created Laplace forces. This couple, as shown in the figure, tends to rotate the coil clockwise, which is opposite to the original sense of rotation. Now, let's apply the right-hand rule to determine the direction of the induced current. Prepare your right hand. Your thumb makes 90 degrees with the other fingers, which point vertical downward because the direction of B is vertical downwards. It is represented by the blue lines in the figure. So, again, the four fingers point vertical downward in the direction of B, and the palm of your hand faces the left side or points to the left, which means that your right hand is in the vertical plane. Now, your thumb must point in this direction, which is the direction of the induced current. Now, look at the coil. The current is in the coil in the clockwise sense. Now, we apply the right-hand rule for F1, but we can also apply it for F2, and in this case, we will get this direction of the current. It is the same.
Number 7. Determine the expression of the current as a function of time and then deduce its amplitude. Using this formula, I is given by the electromotive force E over the total resistance of the circuit, but E is equal to 4 times 10 to the power minus 3 n omega sine omega t proved in part 3. Now substitute n by 245 and omega by 100 pi. Therefore, E is equal to 308 sine 100 pi t. Now replace each physical quantity by each value. So I equal 308 sine 100 pi t over 200 ohm, which is the resistance of the resistor, and 20 ohm is the internal resistance of the coil. Therefore, the expression of the current is equal to 1.4 sine 100 pi t. And the amplitude of the current is equal to 1.4 amperes. Thank you for watching. If you like this video,
subscribe to the channel, hit the like button and share.